Okay, here's some short notes for you about how to do, not how to, that's really the wrong. Let's say some examples of differential equations that come up in the context of physics. For us, there's lots of different examples in the wide-ranging field of physics of applications for differential equations. For us, the way what we're going to see is we know that Newton's second law. Apologies to the very few students who are not in some version of a physics class. Newton's second law is that the sum of all forces acting on some object is equal to mass times acceleration. And this is going to be the jumping off point for all of the differential equations that we look at. So you're going to need to know a little bit about whatever forces are going on so that you can have some version of something here. And then what we're going to find is two examples. We're going to find that the forces here are going to depend on either velocity or position, and if your force depends on velocity, I'll give you examples in a minute if you're confused about what this means. If your force is somehow depends on velocity, then you're going to turn acceleration into dv dt, because that's a differential, because that v will match up with that, and then you can do differential equation stuff that you already know how to do. And if your force depends on position, we're just going to look at one particular example where that's the case, then you're going to turn acceleration into the second derivative of position with respect to time. And we don't really know how to do that by separating variables and stuff. You can't really do second derivative differential equations in that way, so we'll have to think about that in a sec. So here's an example. The classic example of the first, where we have a force that depends on V, is the resisting force, like air resistance. So with air resistance, it should make intuitive sense to you that the faster that something is moving through the air, the more air it's going to crash into per unit time, and therefore the more air resistance it will experience. Just think about sticking your hand out the window of the car when you're going 5 miles an hour versus when you're going 75 miles an hour. So air resistance is often modeled by the force of air resistance is equal to some constant times velocity. Right, so the faster you're going, the more air resistance you have. If something was just falling straight down, then would have a force of gravity on it. And again, for students who don't know this, the force of gravity we model by m times g, where g is our local gravitational constant, 9.8 newtons per kilogram, or 9.8 meters per second squared. Those units are equivalent. But all you need to know is that you're just going to write that as mg, and those are both constants. That's the constant mass, and that's our local gravity constant. And then if there's some air resistance, the faster this thing goes, the bigger that's going to get. And that's equal to BV, Buena Vista. That means that the sum of all forces is equal to this one's winning and this one's losing, and I know that acceleration, that sum of all forces is equal to mass times acceleration. And I know that since I've got a v over here, that's the only variable here. All these other things are constants. So I'm going to make this into dv dt instead of acceleration. And then I just have a separable differential equation problem. Now, exactly how you separate, it's a little bit tricky, I guess. I would first divide everything through by m. So then I have dv dt is equal to, divided by m, that's g minus b over m times v. Now, you can't separate things when you're trying to solve differential equations in this way. You can't separate by adding and subtracting. So I need to move this entire thing over to the other side. So that's 1 over this whole thing, g minus b over mv. dv is equal to dt. Then I'm going to find antiderivatives. This is just a v to the first power on the bottom, so that is going to be natural log. And I just have this constant there. You remember what happens there? I just have to flip that constant over and put it on the outside. You can write out a u substitution there if you need to refresh your memory on how that's going to work. So on this side, I'm going to have negative m over b times the natural log of g minus b over m v is equal to, and on this side, the antiderivative of 1 dt is just t plus c. You'd move the negative sign over, and I'm not going to go further than that in the notes because this, I think, pretty much this exact same problem, maybe this exact same problem I'm going to do for you in the assignment, the video that goes with that. So don't need to do it twice, and I'd like you to be able to give that a shot at finishing this. Just a couple more steps there. And then the other possible thing that happens for us is Hooke's law, which is the, again, apologies to students not in physics class. If you have a mass attached to a spring, and this is like the position where the spring is neither stretched nor compressed. It is the equilibrium position, the relaxed length of the spring. If you move the mass over here, the spring wants to pull it back. And the more you move it, the stronger that pull. And we model that for what we call an ideal or for a linear spring, that the spring force is equal to negative kx. That's called Hooke's law, after Captain Hooke. I'm just kidding. It's not Captain Hooke. Captain Hooke didn't have an E on his name, I don't think. Hooke's law. Here, well, if the spring force is the only is the sum of all forces, in other words, probably gravity and a support force, but those balance each other out. So the spring force is the sum of all forces. So here I could turn that into mass times acceleration. And if I want to go differential equation on this, then acceleration and x are related because this is the second derivative of position. So what did I, sorry. And there we go. And I'm going to move that mass to the other side. And then from here, this is a staring contest. This is not something we can solve by separating. It's something that we can solve by meditating. So what we need to do is think here deeply about what kind of function, what kind of thing, x, when you take the second derivative of x, you get the negative version of the original thing. What kind of function, when you take, who am I? When you take my second derivative, you get negative me. It's kind of like, you know, what is the function that when you take its derivative, you get itself? Well, that's e to the x. So what function, when you take the derivative is equal to negative x. And you can also think about what the position function for this would look like. If you pull the mass off to the side and then let it go, what would that position function look like? That's good inspiration too. So, sine or cosine? Correct. Because if the position is equal to, usually we do the cosine function to model these things because you kind of imagine it being pulled off to its maximum and then time starts there, but it could be sine because that works too. If position is some kind of cosine function, then velocity is some kind of negative sine, and acceleration would be negative cosine. So you can see acceleration is negative version of the original thing. Now, of course, when you pull it off to the side, you're not necessarily going to pull it off to just whatever one unit is. So you pull it off to whatever, like some amplitude there, and that number will just continue to show up. Right, that constant. And then also on the inside, there's going to be some kind of constant. We usually call this omega times t. Actually, I'm not going to do that here. Let's think about this. If in the end, so this is a cosine whatever, and here's the a cosine, so that's like the same thing showing up with the negative sign. But this is showing up. So that k over m, how did that get there? Well, if k over m got there after taking two derivatives, it's because the chain rule happened twice, right? So what would the thing be in here with time so that when the chain rule happened twice, you got k over m? Well, if that chain rule happened twice and you just got regular k to the first power, m to the first power, then this must have been the square root of k over m in here. Because then, when you do it once, take the derivative, you get the square root of k over m, and then when you do it again, the chain rule happens again, and you get k over m, because you multiply by that again. So that's how that works. We're not going to do a lot. Eventually we'll do more with this in AP Physics, but for right now, those are the examples of how differential equations happen in physics. And I wanted to talk about it a little bit now because we're doing differential equations in calculus, and most of you are in physics. So it makes sense to do a little detour into that topic.